Sunny, and in this video, I will walk through the thought of process and logic that inform the way the code for each algorithm is written and how did I analyze each problem in the assignment. The first up is insertion sort. So insertion sort is known for its simplicity. It's shy with the small or nearby sorted datasets, and each element is placed into its correct position. The big O notation in this case is big O of n squared for average and worst case, which speaks to its quadratic time complexity. Despite its inefficiency for large datasets, its ease of understanding make it a staple in algorithm education. And for the logic behind the code reflects a simple iterative process. It starts with the assumption that the first element is sorted. Each subsequent element is placed into its correct position relative to those before it. And it is written to minimize the complexity where possible, favoring the readability and ease of implementation. The code performed very well for nearby sorted data, minimizing the shift required. Next is traveling salesman problem. It is a very difficult problem, seeking the shortest route through a series of cities classified as NP-hot. The brute force approach had a factorial time complexity, so the big O in here notation in here is big O of n factorial, making it impractical for all but the smallest datasets. So my approach focused on demonstrating the computational intensity of such a problem rather than finding a scalable solution. For the logic behind the code right here, it iterates all over permutation of cities, accessing each route length, a clear and direct translation of the problem definition. The code is intentionally straightforward to emphasize the NP-hot nature of traveling salesman problem. It is very impractical for large datasets, highlighting the need for more sophisticated solution. The next problem is summing all value in a 3D array. This problem is a very straightforward task. The time complexity is big O of n cubed, with result from 3 netted loops required for traverse the array. The cubic complexity demonstrates the nonlinear scaling of operations at the side of the array rows. And for the logic behind the code, triple netted loop correspond to the array dimensions, ensuring no element is missed. And the code is structured for clarity, with the netted loop demonstrating the direct relationship between the data structure and the algorithm structure. The next problem is radius short. So for radius short, is offer an interesting diversion from comparison-based sorting algorithm. It's efficient for sorting large datasets with keys or similar length, boasting a linear time complexity of big O of W times M, where W is the key length of the number of digits in the longest number, and N is the number of keys. It is a very compelling demonstration of how non-comparative sorting can outperform order under the right condition. For the logic right here, and the code separates the sorting process into manageable parts using counting sort for each digit, exploiting the fact that integer keys have a predictable structure. The subroutine structure make the code modular and demonstrate radius short efficiency when dealing with the number of similar length. And the last problem is brute force password cracker. So Um, this is a testament for the exponential growth of computational complexity, with time complexity big O um, of big O of k raised to the power of m, where k is the character set size and m is part word length. So this method shows how quickly resource requirement can become untenable. For the logic behind the code, it systematically generates and tests each combination, reflecting the algorithm's exhaustive nature. And the code is intentionally basic to underscore the computational expand or brute force methods. It's a methodical approach demonstrating the algorithm's simplicity and the trade-off between time and computing power. That's it for the assignment.